Hello. Good afternoon. Welcome to Krishna's class. So let us continue with the proof of the completeness of LP. In fact, we left it in the with one part left out. In fact, what we have proved is that we proved LP mu is complete for less than infinity. In fact, we left out the case where p equal to infinity. Let us briefly recall what we did. We considered a Cauchy sequence in LP, and then we constructed from it a monotone sequence Fnk, and what we proved was from this, we constructed a monotone sequence Fnk from it, and then we considered the construction of a function f from it. And then we had a situation like Fnk this is equal to Fnk. This is for k equal to now you see that we have proved that we considered the sequence Fn1 or the function Fn1 plus infinity and this we proved that converges absolutely and for almost see the proof, the details of the proof in my last lecture. Now the partial sums of this is what I have written here, and we have fx defined by limit n tending to infinity f almost every. Now this is what we proved that. So then we in LP. This proves the completeness of So we started with a Cauchy sequence and then found out a limit, and we proved that converges to Fni, the subsequence Fni converges to F in LP. And this is how we proved the result. And then naturally F is the LP limit of F Fn, or the given sequence. That is the result that we have. And the other things are technical. Now what we want is the following. We take the case P equal to infinity. That is, we look at the completeness problem. Now recall that the this is the norm that we are using. So what is given is given epsilon where x is a n depending on epsilon such that this is what we mean by Fn is a Cauchy sequence. L infinity. Let us now try to construct an F to which this sequence would converge. So claim this is what we want to prove. So we have to identify a particular F as we did in the previous situation. So let us work on that. Now remember, these functions Fn's are all what you call essentially bounded functions. Now given Fn, essentially bounded that is because since this property is okay, therefore define AK as the class of all x belonging to x for which now you see that we have fkx is less than or equal to norm of fk infinity for almost all x. This is what we know because of the supreme one law. Okay. Therefore, we designate AK in this way. Similarly, let Bmn be defined by Bmn, which is a subset of x since these functions fn and fm are L infinity functions, their essential supremums are bounded, and you see that the set of points on which fn minus fm is greater than fn minus norm of fn minus fm is a set of measures 0. So also the same thing. So this is again because Therefore, sets of measure 0. Okay. Consequently, so let E be the and B and for until then measure of E equal to 0. It is the union of this class and this class. Okay, each one is of measure 0. Therefore, this is a countable union of measurable sets is measurable and its measure is less than or equal to the sum of the measures of that. Each one has measure 0. Therefore, the union of these sets denoted by E also has measure 0. Now, on the complement of E, complement, the sequence converges uniformly bounded function to a bounded function. This is the important part. Now, this is the important inference. So, that's how we fix f. So, we have these functions, each of these functions converges uniformly, or the sequence of functions f1 converges uniformly to a bounded function on f. So, there is uniform convergence to a bounded function on E complement. Naturally, f belongs to L infinity, and goes to 0 as n comes to. So, this completes the proof of the completeness law. complete. So that completes the proof. Okay. So we have proved in all cases. Therefore, we have now complete for every so that completes the proof of the theorem. Okay. Now we take a spin-off result from what we have proved. Now this is given in the form of a theorem. If less than or equal to infinity, and if is a Cauchy sequence LP with which you have already proved that it exists. Okay, that's how we have proved that there's a this Cauchy sequence converges in LP mu, and the limit is given by some f. Okay, so f belongs to LP. Then Fn has a subsequence which converges to f almost everywhere. Converges to pointwise. In fact, we have proved this theorem as a part of the results because you go through the construction. We constructed a subsequence which converges to a function f under the assumption that it's a Cauchy sequence, and so it comes out from the proof. So proof this appears in the proof of the we actually constructed such a subsequence. So the proof is already done. So we will not repeat it. We will just leave it as it is. Okay. Now we prove another result. Now these are all useful results. We want to show that there exists a credible approximation to these functions, to such functions using what are called simple functions. Okay. So the next theorem, s are equal to infinity, can be approximate as closely as we like using simple functions. Or in other words, the space of all simple functions belonging to LP mu is dense in the space LP mu. This shows the density of simple functions not zero on finite measure, not zero on a set of finite measure. So let us state the theorem now. Okay, so we give the statement of the theorem. Let class of all complex measurable simple functions X such that the measure of the set is not equal to 0 is finite. If is dense in LP. Note that this result is stated only for the case 1 lesser or equal to less than infinity and not for p equal to. So let us prove this here. What do we mean by simple functions? They are functions which takes only finitely many values. Okay. And the assumption that we are making is that the set on which the Sx is not equal to 0. The measure of that set is finite. Okay. So that's a restriction that we made. So there are two things. These functions S take only finitely many values. They are complex valued, measurable, simple functions on X. And the set of points in X where Sx is not equal to 0, okay, has finite measure, right? Therefore, then we prove that such a collection of functions is essentially dense in LP. In other words, when you do analysis, you can take such functions and work on them because the integration is easy on them, etc. It's quite easy to work with this dense class of functions. The advantage of working with the dense functions of a very clearly known class, okay, either they are simple functions or continuous functions, then or differentiable functions or C infinity functions. In all these cases, there are some properties available on that which you can exploit while doing analysis on that. And because of the density, you can just prove it on this class. That will be easier, and then push through a limiting argument and explore whether it is valid for all functions or not. This is the advantage set. Okay, so that's why we search for some credible and useful dense subsets of LP. Okay, where if certain properties holds using the limiting property, we may be able to push it across to or prove that it is valid for every element in LP. So that's the whole advantage. And this simple class of functions with this particular property is something very useful in this process. So let us prove this result. Proof is very simple. It uses Fatos's lemma at some stage. What is called the bounded convergence theorem is some stage. That's all. Okay. Why it is in LP mu? Because you see that S is a bounded function because it takes only finitely many values. Therefore, it is a bounded function. Clearly. Further, the set on which it is not equal to 0 has measure finite. Therefore, what you have is this integral d is equal to this is equal to the set on which set on which equal to 0 Now, what you observe is this, that this part is 0. This part is 0 because it is whether this set is finite or not has finite measure or not finite measure. You see that this part is 0 because S is 0. Okay. Therefore, this is equal to integral over x belonging to x not equal to 0 of and you know that Sx takes only finitely many values. Therefore, this is less than or equal to sum m into measure of equal to 0 and that is finite. Okay. Therefore, so that is okay. Now you take now we work with we are to work with complex functions, but we develop the proof. Look at the situation when f is positive. Suppose greater than or equal to 0. And f belonging to LPU. And Sn be a sequence of simple functions as we have constructed earlier while defining the integral. Measurable. Now you recall that I'll just demonstrate what we did. See, suppose you had a non-negative function. So first we looked at 0 to 1, and on that we defined the set of points where f is equal to 0, the set of points this half is less than or equal to half, and the set of points where is less than or equal to 1, and then beyond that so we could essentially build a function in the following form. See, here on this set where it exceeds 1, we define the function to be. Okay. Where it exceeds half but lies in half, we define the function to be half. So you see it's half here, it's half here, and also so you have now a simple function defined as 0 here, half here, 0 here. So it is 0 here, 1 here, half here, 1 here, half here, 1 here, half here, 1 here. This is how the function is defined. That is f1. Then f2, you go to the next level, that is up to 2. Allow the function or take it as a bound as 2, and with 2 and partitioning from 0 to 2 into 1 by 2 to the power 2 square, we get this 1 by 4, 1 by 2, 3 by 4, 1, 5 by 4, what is that? 3 by 2, and then 7 by 4, and then of course 2. This is the partition that we do, and do the same thing like this. So we construct a sequence of functions SK. Right? They are all simple functions. Now we have the function is always bounded by f. Okay, so it is an approximation from below to the function, right? And we have LP. So we can actually construct a sequence of simple functions using the process that we have already explored while defining the integral. Okay. Now observe that modulus of here we have assumed f greater than or equal to 0. F is non-negative. Therefore, this estimate is there. Now apply dominated convergence here. You get norm of f minus Sn goes to 0 . What is happening is, you look at this sequence. See, what you get is this. So you have f minus Sn almost everywhere by construction. Okay, and then you also have and they are all functions in S, the class that we have looked at. Is bounded by this is true, and therefore to take the integral of this, okay, goes to the power p, and this you see, this goes to 0 almost everywhere, which implies norm of norm of f minus f belongs to the LP closure of now we have proved it for the case f greater than or equal to 0. Okay, so we can prove it for all real valued functions by taking its positive, by taking it, writing it as the difference of two non-negative functions. For each non-negative part, the result, and then go to the next level of working it for complex functions. Okay, or you get this really. This is what you want to. You are a complex function, then you come to a real function, and this is non-negative function. Okay, so you can look at this sequence, and from that you can take the inference. Okay. Okay, so that completes the. So we have got some very nice class of simple functions which do approximate to a given LP function. So with that we conclude today, and now we go to study the similar problems with more structures on X. Here we don't have any structures, extra structures on X, except that you have a, it's there's a measurable class of the sigma algebra of measurable functions, and mu is defined on that. Okay, so thank you very much.